Today we are going to look at chemical equilibrium. I hope everyone's got the study material. Now, every one of you, I think, know by heart the definition, right? It's that two easy marks. The rate of the forward reaction is equal to the rate of the reverse reaction. But there's two things that we need before we can get to equilibrium. And the one is that you have to have a reversible reaction. Some reactions can't be reversed. Right. If you took a piece of meat and you fried that piece of meat, you can take the gases and you can put the little drops of fat back. Will it go back to raw? No way. Some reactions just can't go back, right? So you need a reversible reaction. How will I know if a reaction is reversible? There's no way that you can know. You will have to go to the equation and see that double arrow, right? If you've got a lot of experience in chemistry, you might look at a reaction and say, I think this one's going to be reversible, right? But otherwise, just look at the arrows. Double arrows will indicate. And then you also need a closed system. If you have some of the reactants or the products escaping, then obviously the reverse reaction can't happen. So you need a closed system. So those are the two things that you must have before you can have equilibrium. And now we're going to start with our first example. Right. Let's take that equation, and what we are going to do is we are now going to add to a sealed container only nitrogen and hydrogen. So you must be able to read between the lines. They're adding nitrogen and hydrogen. What are they doing that they don't tell you? They are not adding NH3. Right. So, no NH3 at the start. No NH3 at the start, right? They don't tell you, but you have to know. If they only tell you they put N2 and H2 in, they're not putting NH3 in. So you start with what they put in. So they put only the things on the left-hand side. So if you look at this reaction, N2 and H2 on this side, they put a lot of N2 and H2 in. So what does that mean? I've got a lot of reactants for the forward reaction, right? And if I've got a lot of concentration for forward is going to happen fast. So what's going to happen? Now, you have to draw your own graph there. If I look at the rate of the reaction and the times, the forward reaction will have a big rate. It will be happening fast because it's got things to happen with, eh? You've got a big concentration of your reactants. So that one will be happening fast. Now, what they did not tell you, but what you know, is there's no NH3 in that container. So how about the reverse reaction? If you've got no NH3, and we are now looking at the reverse reaction, can it happen? Rate is 0, because I've got no NH3 molecules to collide to make this reaction happen. So if you look at the rates of a reaction, the reverse reaction will have a rate of 0 when you start out. Okay, so now things are going to happen. You have the forward reaction happening and the reverse reaction not. Right. If the forward reaction is happening, it's going in that direction, right? The forward reaction is using N2 and H2. So what's going to happen to my N2 and H2 concentration? It's going to decrease, right? And if this decreases, then the forward rate of reaction will decrease because it's got less things to happen with, right? So the forward rate will be going down, right? Now, I don't know if you've got a second color. Maybe a second color would be nice. Otherwise, use dotted lines for the other one. We start out, and at the start, you've got no NH3, so the reverse reaction is not happening. The rate at which it happens is 0. But now, as the N and H react, it is making NA3. So now you can have the reverse reaction happen. And the more NH3 that is formed, the faster the reverse reaction. So the reverse reaction will increase, increase, increase. Right. So this is actually just from the table above. So when we start out initially, you've got high concentrations of N and H. That was what we put in. And then that makes the forward reaction fast, and you've got a big rate. But initially, have no NH3. They didn't put anything in there, and therefore no reverse reaction, 0 rate. But then as it happens over time, what happens over time is you are now using the N and H, so N and H will decrease because it's used, and that makes the forward reaction go slower because it's got less concentration to happen with. And then, as this forward reaction happens, you get NH3, and the NH3 will become more and more, and therefore the reverse reaction will increase. And then finally, we get to this stage that we call chemical equilibrium. And at chemical equilibrium, now the forward and reverse reactions are at the same rate. At the same rate. So for every N that is being used in the forward reaction, there is an N formed in the reverse reaction. So the amount of nitrogen is going to stay constant. For every single one that goes away, one comes back at the same time. Huh? If you've got 2 going away, you've got 2 coming back. Same rate. Right. So now the concentrations are not changing, and therefore the rates are not changing anymore. So now you have the rates constant. Right. So this is just actually an explanation of that equilibrium definition. What happens is this, and now you understand the graphs as well. Hey. Right. Now, when we do this, you have this equation, and why, usually, do we do a chemical reaction? To make money. Right, to make money, right? You want to produce something to put into bottles to sell. Is that right? You want to produce NH3 because you can sell it to the guys who want to make nitric acid with the what process? Ostwald process, hey? Fertilizer. Okay, never mind. But you want to make a lot of NH3 because the NH3 is the thing that you want to sell. It's going to make you rich. So what we now know is not all the N2 and the H2 that you put into the container is going to end up as NH3. Some of them are going to stay in N2 and H2. When you get to equilibrium, there will be N2s, there will be H2s, and there will be NH3s. So now, before I start building a plant to produce something, you want to know, is it worthwhile if from hundreds and hundreds of tons of reactants that I put in, I only get a few grams of product, then it might not be a good thing to try to do. It's not economically viable. Right. So how do I know how much of what I put in is going to end up in the product? You look at the Kc value, right? That equilibrium constant down there. Right. Because the equilibrium constant is going to tell you when you get to equilibrium, what is the ratio, and that is a very important word, ratio. What is the ratio of the concentration of the products to the concentration of the reactants, right? And it's all about the ratio. So if you get, okay, and just remember the brackets are for concentration, and give me a quick formula for concentration. How do I calculate concentration? Yes. That's good to hear. You're up and around. Okay. C equals N over V. Right. And pure solids and liquids that are actually solvents are left out. But you've done a lot of that in school. We're not going to look at that. That's the easy part. Hey, let's talk about the Kc. If the Kc value is big, it's more than 1, then it tells you that the top number is bigger than the bottom number. So more of the things are in product form. So if I want to build a plant to produce something, what do I want? Big Kc value. Right. What big Kc value will tell me most of the things are in the product side. Right. That's what I want, a big Kc value. So when you start out, now you, the chemical engineer, they're telling you, you must design the plant. So the first thing that you go is you go and check the Kc value. Right. Now, we used to go to the library and get a big book with a lot of Kc value and to check up the Kc value. Now what we do, we Google. Hey, Okay, but if you Google and you get the Kc value for an equation, right, what are you going to get? Pages and pages with Kc values. Why? Because the Kc value is only true for a specific temperature. Right, so at every temperature you have a different Kc value. So you're going to get lists and lists and lists and lists and lists, and then you must decide, at what temperature am I going to work, right? And remember, to get a higher temperature, you have to buy a lot of coal, and you have to have a plant with a furnace and things like that. So the chemical engineer is going to say, a little bit more product for how much more expenses and things like that. But they use the Kc value to know how much of what I put in is going to be in the product form at a specific temperature.
All right, just a few questions to practice this. First one there, write equations for the equilibrium constant for the following reactions. Check the first one. To write the Kc expression, look at it. Liquid does not come in, so we will have O2 products divided by reactants, H2O2, and the 2 in front becomes a square there. Right, next one. Solid. Solid has got a concentration of 1. It doesn't come into the Kc expression. So the Kc expression will just be Ag plus Cl minus concentrations. Next one, no liquids, no solids. So the Kc will be O2 to the 6th divided by CO2 to the 6th. In number 1.2, ammonia is prepared according to the following reaction. You give the reaction, and then they tell you that at a high temperature, the equilibrium mixture, which is very important. The values that they give you for concentrations are true at the equilibrium, because in the equilibrium constant, you need the equilibrium concentration. So that's NO3, NH3 to the square second times H2 to the third times and 2. Right. And then since we have concentrations at equilibrium, we can just substitute. So that will be 2 squared divided by 1.5 to the third times 0.5. And when you work that out, you end up with 2,37. Moving on to number 1.3, hydrogen iodide can be produced by the following reversible reaction, and they give you the Kc value is 56 at 425 degrees Celsius. And now they tell you that at a certain time during the reaction, the concentrations in the container are, and they give you all the concentrations. And now the question, do a calculation to determine if the reaction has reached chemical equilibrium. Now, what do I know? When we have reached equilibrium, my Kc value, 56, will be equal to Hi squared H2I2. That is my equilibrium constant expression. And if that is equal to 56, then I am at equilibrium. So let's check. Hi, 2.5, remember to square, H2, 1.5, I2, 0.1. Okay, when you work that out, you end up with 13,50, which is not equal to my Kc value of 56. And immediately I will deduce that chemical equilibrium has not yet been reached. Right, moving on to number 1.4, consider the following reaction. 2A plus B gives C, all of them gases, so they're all in the equilibrium constant equation. And they tell you that 2 moles of A and 10 moles of B are sealed. So this is what you put in, right? And then at equilibrium, you have 4 moles of A. And remember, when we do the Kc expression, now let's start with the Kc expression. That will be C concentration divided by A, and the 2 becomes a square, and B. Right. Now, if you look at this, what do we need to put in here? We need the equilibrium concentrations, right? We need equilibrium concentrations. Now there, they gave us A at equilibrium, but for A and B, they also gave us what they put in, not what is at the equilibrium at the end, right? So what's nice, if you take a block and you keep book of what you've got and what's happening and what do you start with and what's reacting and what do you have at equilibrium. Now let's take our equation, 2A plus B in equilibrium with C. Then I can keep the first column for A and B and C. And in here you will see they are reacting in the ratio 2 to 1 to 1. Now let's read again. 12 moles of A and 10 moles of B are sealed. Right. So you've put in 12 moles of A and 10 of B. And then you have to read between the lines, because they don't say anything about C. So what can I know about C? If they only put A and B in, there is nothing of C in that container when we start, right? And then they tell you that at equilibrium, you've got of A 4 moles, right? Now, immediately there you've got a column where you've got more than 1, and that will tell you something. If I start with 12 and I end up with 4, it means some of this was used during the reaction, right? So I'm going to put a small minus there. Most memos and teachers leave it out, but I like it because then I know if that is used, then obviously B must also be used because they're on the same side. If I do the forward reaction and it takes away A's, it will also use some of B, and then it will produce C. Right, now if I start off with 12 and I end up with 4, how much was used? Subtract, giving me 8. Right, and the moment you've got that 8, then I will say this makes it easy because I know it reacts in the ratio 2 to 1 to 1. It reacts according to your equation. Now this is the only row that's going to have the same ratios as that because it reacts according to the reaction. Remember, the first one was what you put in, and that depends on how that guy who was putting it in, what he decided to put in. It's got nothing to do with the equation. And also, if he put a lot of B extra, then I will have at equilibrium a lot of B extra. So here it won't be in the ratio 2 to 1, and there won't be in the ratio. The only row that will be in that ratio is the react row. So if 8 of these react, how much of that will it take with you? According to the equation, 2 of that will require 1 of that. So if I take 8 of these, 4 of those, 2 to 1, same ratio, 2 to 1. And that will make C's, and how much? 2 to 1. So it will make 4 of C. So now I've used the ratio to get the other moles that react. And now I'm going to say, okay, if I started out with 10 and 4 was used, it means I end up with 6. If I started with 0 and I gained 4, I'm ending up with 4. Now I have to get the concentration by dividing by the volume. Volume, yes, over there, right? So I have to divide by the volume, which means divide by 2. So I end up with 2, 3, 2. And then if I put it in here, C being 2, A being 2, and remember to the second, and then 3, and then you end up with 0,17. And there I've calculated the Kc value. So this block is just one nice way to keep track of what did I put in, what reacted, and what do I have at equilibrium. And the reason for this is I need the concentrations at equilibrium. Right, in the next video we will start with Le Chatelier's principle.